All right, we're going to be looking at a really good textbook, but also one that's a little more at the graduate level and a little more challenging, which is called Optimization by Vector Space Methods by Luenberger. So I'm going to write that up here. Here's the book we're looking at, Optimization by Vector Space Methods. This is going to be by David G. Luenberger. So we're going to be looking at this book in a good deal of detail. Now, actually, there's like a very big section at the beginning that just talks purely about notation. We are actually going to go through that line by line, talking about all the notation, and then we will only, at that point, be able to do a little bit of the first chapter. So here's the notation. So there are some very helpful headings in this book that clarify what each part of the notation is about. These headings are really good because if you don't read them, it starts to feel like all the notation is almost the same, but somehow it feels almost repeated but slightly different. So what's good to recognize is that they're actually talking about different things. So first section is called sets. So right now, set your mind to think about a set. So here it's going to say if X is a member of a set, X is a member of the set S, we write X is contained in S. That's the notation that they're going to use. And then if you say, for example, Y is not contained in S, so you put the not through that, then it means Y is not a member of the set S. Okay, great. So, next one. A set may be defined by, so here's different ways that you can define sets. Remember that this means set. So a set may be defined by listing its elements between, I'm going to use this abbreviation here, between braces. So that would be, here's an example. If you have a set and it consists of 1, 2, and 3, here S is equal to 1, 2, 3 in braces. Okay, that's one way. Next way. You can also have a case where you have S is specified as consisting of all elements of the set X with property P. Let me say that one more time. S is specified as consisting of all the elements of the set X with a given property P. So if you want to say, okay, then that makes a set. You have some set and you take some of at least some or all of the elements of that, and you say all the ones from that set that have this property. So you can write that as saying S is equal to all the elements in X such that P of X holds. So P of X might be something like X squared is less than or equal to 5, or something like that. So that's what this means. So you would write something like that. That signifies a set. It's just defined in that way. And then if you actually know what X is, then you can just write it like this. You can say X such that P of X, if this large set X is understood, a lot of times it's good to avoid ambiguity and put the X. Okay, great. So now we're going to talk union and intersection. What is that? So a union of two sets, S and T, is denoted by S union T. If you want to try to remember, just think union has a U in it, so then S union T makes sense. And then so this consists, the union of two sets consists of all of the elements that are in either set. So if it's in S, it's in the union of S and T. If it's in U, it's in the union of S and T. Or sorry, if it's in T, it's in the union of S and T. If it's in S and T, it's in the union of S and T. So regardless which set it's in, it has to be just in one or the other, or both, it doesn't matter. Okay, intersection. So the intersection of two sets, S and T, is denoted like this, which does kind of, I don't know, in my mind that does kind of look like two things like somehow coming together. So this means intersection. So intersection consists of all of the elements in both S and T. So in this case, it will mean like if it's in only S and not in T, it's not in the intersection. It has to be in both of them. So two sets are called disjoint if the intersection is empty. So you can also have empty sets. So if they don't intersect anywhere, there's no 2 points, there's no 1 point even that's in both sets, then those two sets are disjoint. their intersection is empty. So if S is defined as a subset So if S is defined as a subset of the elements of X, then we can define what's called the complement. So notice that it's a subset of the elements of X. It is important when you talk about complements because you're going to say that the complement is everything in X that's not in S. If you didn't define that S is a subset of something, that's kind of an ambiguous thing to talk about. To talk about a complement of something where you don't know, like the complement being everything that's not in S, but where is it then? So what you need to do is, it is important to say what it says here. S is defined as a subset of the elements of X. So then you say that its complement is going to be denoted as with like a tilde, or depends on the book what you look at. Here they're doing it with this tilde. Consists of, this means complement of S, consists of those elements in X that are not in S. So here's what I said. If you don't define that S is in a set X, then what would this even mean? Because it needs to be the elements that are in that set that are in S. So you have to have there be this X. Okay. The next point is that a set S is a subset of the set T if every element of S is also an element of T. So then we write it like this. So you can write S is contained in T, or you can do the opposite way. I very rarely see this one, but just be familiar. This is much more common. This is the way we're going to write it in our own work. But if S is a subset of T, but it's not actually equal to T, then we call S a proper subset. So at least in this book, they're allowing S and T to be equal with this notation. But then if they're not, then we say that S is a proper subset of T if it's only sum of T and not all of T. Okay, now we're going to do a set of, so that was specifically about sets in general. That was set notation. Now we're going to talk about sets of real numbers. So a very specific case. So now we're going to do sets of real numbers. This is a very specific type of set. So if A and B are real numbers, then we're going to have stuff like this. So here's AB with the bracket. This is going to denote the set of real numbers X. So this is the set of real numbers X satisfying that A is less than or equal to X is less than or equal to B. If you do it open, then that means that you have not a strict equality here, then it will be the set of real numbers X satisfying A less than X less than B. And then you can have like part of it open, and then that will mean, like this one for example, would be the set of real numbers X satisfying A is less than X is less than or equal to B, etc., etc. So now we're going to say if S is a set of real numbers bounded above, so it's only sum of the real numbers with a bound above, then there is a smallest real number y such that all of the x's in the set are less than or equal to this y, and y is called the least upper bound, or supremum, of S, and it's denoted by the supremum of X contained in S of X, or the supremum of X such that X is contained in S. So this is important because note that supremum is not the same as max, because here it says the set of real numbers is bounded above, then there's a smallest real number such that all of the points in that set X are less than or equal to Y. If the set is actually open, then it doesn't actually reach ever like a biggest point exactly. It is bounded above, so the number that's like the upper bound, like if you have something like A, B. Okay, so the number B is the upper bound here, but you're not allowed to actually reach B in this set. So B is the supremum here, but it's not actually the maximum, because the maximum implies that you actually got there. And then so last part for the moment is, so if S is not bounded above, we write that the supremum of X over the set S is infinity, and that's just how we're going to define notation. And there's also a greatest lower bound, which is called the infimum for a set S, and is denoted the infimum of X contained in S of X, or the infimum of X such that X is in S. Okay, great. Thank you, everyone.